Hi guys, today I'm gonna start talking about integration. So just like when you have addition, the reverse operations, subtraction, addition, subtraction, they have multiplication, division. So division is the reverse operation, multiplication. Okay, same thing for integration and differentiation. So when you have a function, okay, and you differentiate it, it becomes the derivative, right? If you want to do the reverse thing, you integrate. I'm gonna say yes. So it's integration, okay? Integration. Or I could do this. So integration, all right? It's also called anti-differentiation, right? And differentiation, like that. Okay, so integration or anti-differentiation. When you have a definite integral, then it's called integration. When you have an indefinite integral, it's called anti-differentiation, but it doesn't really matter, okay? So how do we do this? Well, let's say that y equals f of x, okay? And then when you do dy dx, so you're differentiating y with respect to x, it becomes f prime of x, okay? So look at this. You can say, because what is dy? dy in this case, it's a very small amount of change in y. And dx is a very small, it's an infinitesimal amount of change, or infinitesimally small amount of change in x, okay? So this is a very small amount of change in x, and this is a very small amount of change in y. How small? Infinitely small. So this is an infinitely small thing here. And then you have the differentiation here, which is f prime of x. Fine. So let's just get this stuff over here, okay? So we can say that dy equals the f prime of x dx. Now you can integrate this stuff, which is the anti-differentiation. So the symbol is this one, all right? Kind of looks like I don't know, one of those things, one of those sticks that old people used to walk, you know, I don't know. So you have this, you integrate here and you integrate here. Now when you integrate dy, okay, and you're integrating this dy with respect to x, well, you had differentiated it with respect to x. So this is just becomes y, okay? And here's the thing. You have the integration of f of x. What is this stuff in here? This is going to be like a dummy variable, but it's not a dummy variable. This is actually an infinitely small amount of change in x. But you see, when you have a function, you got to differentiate it with respect to something, because there are some functions that have two or more independent variables. We're going to see that way later, okay? But this one only depends on x. This function here and this one here, it only depends on x, doesn't depend on anything else. So you're integrating with respect to x, okay? So when you do that, well, you had differentiated this one with respect to x and you got that. When you go back, you're just going to have f of x, okay? I'm going to put an x here because it looks like a y. So what you're going to have here is f of x. But there's something, you got to put like a plus cy. Because you see, when you're going back, you don't know if there was a constant before. Let me show you guys something. Let's just say that you have y equals 3x squared, okay? You differentiate it. I'm just going to put y prime. It's going to be equal to 6x. So what do? You multiply by this and you reduce this by 1. Okay, so you got to do the inverse thing. You got to increase it by 1 and divide. So you're going to increase this, integrating this. Okay, now we're going to integrate this, and we're going to integrate it with respect to x. So it's kind of good to put a dx in here. What are you going to have? You're going to have y equals, so the power here is 1, or we're going to increase it to 2, so it's going to be 6x squared, and then we have to divide it by this 2. Okay, So when you have 6 divided by 2, you have a 3x squared here. There you go, 3x squared. So this is the original formula. Okay? Now, let me show. So this was the formula. I'm going to put like y sub 1 equals, oh man, equals 3x squared. Now let's put y sub 2 equals 3x squared plus 5, right? When you differentiate it, so now we have y2, 3x squared plus 5, okay? And then you differentiate the thing, this becomes 6x, and this 5 is cut away, right? It's just gone. Okay, so you have 6x, and then you're going to integrate with respect to dx, and you have 3x squared. Is this the same function as this? No. Okay, so that's why, because you're losing this 5 in here. Where's the 5? The 5 is not here. Okay, so when you integrate, you have to integrate and you have to put a plus c. How am I going to find out what this c is? Well, then you're going to have initial conditions, like for a certain x, for example, x0, you had y0, and for x1, you had y1. So these are called initial conditions, and based on these initial conditions, you're going to be able to substitute that in the formula and get the exact c, okay? But generally, when you're just integrating stuff, you have to integrate blah, 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 plus c. There's always a plus c in the end, okay? But right now you cannot, so far in this course, we're not going to see how we're going to find this c. Maybe, at least not for now. So what is the integral of 6x? The differentiation, okay, 3x squared, because I talk too much. So differentiation of 3x squared is 6x. Now, the inverse, let's call it integration. The integration of 6x is actually 3x squared plus c. Because you don't know if there was a c here. Wait a minute, what if there's no c? Then there is a c. 3x squared equals 3x squared plus 0, okay? So this 0 is the c. All right. Okay. Now, yum, yum, yum. So let's just do a few here, okay? Oh man, y equals 2. All right, so what is this? This is the same thing as 2 times x to the 0. All right, so integrating y with respect to x, what are you going to have? Well, you have to increase this by 1, okay? So it's going to be 2 times x to the 1, because 0 plus 1 equals 1. And then you have to divide by this sum. 0 plus 1 equals 1. So we have to divide by this 1. Well, we're going to divide in here, which is 2x. So the integration of y with respect to x is 2x plus c. Never forget the c, okay? Then there are going to be some like some things in here. Stuff like this. This is what the book shows, okay? I'm gonna let you guys pause the video. This is just a differentiation integration table. So if you guys want to pause the video and take a screenshot of that, I don't know. I'm gonna give you a second. Okay, so you see here the derivative of kx with respect, everything's with respect to x, okay? So dkx dx is going to be k. Over here, you integrate k, you get kx plus c. You can see that it's always the inverse. So k f of x becomes k f prime of x. Integrating that, you have k f of x. All right. Differentiating f of x plus or minus g of x, you got f prime of x plus or minus g prime of x. Integrating that, you can integrate it separately just like you differentiated it. So you have f of x dx plus or minus the integral of g of x dx. The derivative of sine of x is cosine of x. The integral of cosine of x is sine of x. So it's just going back. okay? The derivative of cosine of x is minus sine of x, so the integral of sine of x is going to be minus cosine of x plus c. You can see that you always have this c in here, okay? So the tangent is going to be the secant squared. Integration of the secant is the tangent plus c. Secant, you got secant tangent. The integration of secant tangent is going to be secant plus c, right? Cotangent minus cosecant squared. The integration minus cosecant squared is going to be minus cotangent plus c. So there you go. So let's do a few things, a few more examples, just to train, to practice. So 1 divided by x cubed, okay, integrate that. Okay, so integrating, okay, well, you know what, I'm just going to do this. Yeah, I'm going to do this. So what is this? It's x to the minus 3, okay? So what you got to do is to increase by 1, okay? So x to the minus 3. So you do plus 1 minus 3 plus 1 minus 2. So you divide by this minus 2. All right? So what you have in here, in the end, you're going to have minus 1 divided by 2x squared. Yeah? Now, square root of x. You want to integrate that? Oh yeah, I forgot. Plus c. Okay, there you go. So what is this? X to the 1/2. So you want to increase it by 1, which makes it x to the 3/2. And you have to divide. So it's going to be 2/3 plus c. Okay? Let's see now the integral of 2 sine of x. Okay, you can take the constant here out of the integral. Okay, so it's going to be 2 times, what is this, the integral of sine of x? It's going to be minus cosine of x. So minus cosine of x. Yeah, and for example, let's just say that we're talking about the chain rule, okay? When you differentiate, look at this. You want to differentiate sine of x with respect to x, okay? You want to do that. So this is the outside formula, and remember that this was the inside formula because you're not differentiating with respect to sine of x. You're differentiating with respect to x. Okay, so sine is the outer formula or outer function, and the x is the inner function. So you want to do cosine of x times the derivative of the inner function. Now, what is dx? Dx is 1, okay? So there you go. So when you want to integrate cosine of x, what you got to do is to integrate the outer function and divide by the derivative of the inner function. Why? Because when you differentiated it, you multiplied over here by the derivative of the inner function. So it's going to be sine of x divided by the derivative of the inner function, which is what? 1. Okay, dx is 1, so you divide it by 1, which equals sine of x plus c. And here you got minus 2 cosine of x. Oh, okay, so here's the same thing. Minus 2 cosine of x divided by the derivative of the inner function, which, because it's x is just 1, I'm going to leave it, so plus c. You can always do this too, guys, like the integral of dx. What is that? Well, this is just 1, right? So you can say that this equals x plus c. Why? Because what is 1? 1, okay? This equals 1d. Okay. It's because I want to go too fast. Okay, this is the integral of 1 times dx, which equals the integral of 1 times x to the 0 dx, which equals x to the 0 plus 1, 1 divided by this 1, okay, you have x plus c. So the integral of dx is just x plus c. The integral of x plus 2 dx. So do that. Okay, so I'm gonna do it, okay? X squared divided by 2 plus 2x plus c. Another one. The integral of 3x to the 4th minus 5x squared plus x dx. Do that. Okay, so it's going to be 3x to the 5th divided by 5 minus 5x cubed divided by 3 plus x squared divided by 2 plus c. Yeah. There's something that I want to say, guys. Differentiation is kind of always easy to do, but integration is not always easy to do, because you go like, oh, so integration's easy. No, there are some integral calculators, and then you start with something simple. For example, the integration, I don't know, I'm just blurring it out here, because later in the course, there's an example that I did in the integral calculator. I think it was the integral of tangent of theta with respect to theta, or it was the tangent squared of theta. And then what you're going to have is a huge function, huge. You have over 100 steps or maybe 200 steps. So from here you get to this point, and from this point you get to this point, and from this point you have 3 ways, okay? 3 different ways of getting to the same point here, and you can choose which one you want. And then from here you go there, and you keep coming to this point. And every time that you get to one of these points, you have to do that substitution thing, right? So you start with y, which is a function of x, but then it's not actually a function of x, it's a function of g, of h, of I, of x, and then I have to go 2, 3, 4, and then I have to say, okay, I of x equals u, and then I have to say that h of u equals omega whatever. So you have to keep making, you make a substitution here for u, and then you got to make another substitution here for omega, and I make another substitution here. So after you integrate, you have to keep back substituting everything, okay? So something like this, I don't know if this is the exact example, but this looks so innocent, right? I mean, it's the integral of the tangent squared of theta with respect to theta. You think, oh, that's good. No, it's huge, okay? And I'm going to explain why. And they have many, like, if it's a trigonometric thing, you're going to use a strategy to integrate. And when you have, I forgot what I was going to say, when you have the trigonometric thing, okay, and then there are going to be some things that are just weird. Well, I forgot what I was going to say now, but you got to use different strategies for everything that you're going to integrate, okay? And sometimes it's not easy, because you see, look at this. Let's just say that, oh yeah, you got integration by parts, okay? Why? Because look at this. The ln of x, when you differentiate this, okay? When you differentiate this, you have 1 divided by x. Remember, if you guys don't remember, go back and weigh in the videos. I think there's one of the videos that not from this playlist, but from another playlist like mathematical proofs, math proofs, that I proved that ln of x differentiating, you got 1 divided by x, okay? But is this all? no, it's not, because you're differentiating this with respect to x. All right? So when you integrate this stuff, this dx comes over here and multiplies by this 1. So you're integrating dx, 1 divided by x dx, right? Now let's just say that you're integrating 1 divided by the cosine of x. How can you do that? And you go like, okay, actually this is cosine to the minus 1, but then you have to integrate, and the outer function is the cosine, and the inner function is this one. So how do you do this? Well, you see, let's just say that u equals cosine of x. Now, what do we have here? We have the integral of 1 divided by x times dx. So we can say that this is the integral of 1 divided by u times du, right? Wrong. Where's du? You don't have du. Over here, I'm saying that you have dx. Why? Because 1 divided by x. What is dx? You're multiplying this by dx. What is dx? If you have x and you differentiate it with respect to x, you have a 1. So you got a 1 here, so you have a dx, okay? This 1 divided by x, it's actually dx over x. This is what you're integrating. Now, when you do this, okay, you come over here and you say that cosine of x equals u, and then you're going to integrate it with respect to u, okay? So you have a u here. Now, where's the du? Okay, so du was going to be minus sine of x, okay? Because if u is cosine of x, du, you're differentiating, is going to be the minus sine of x. If you had a minus, I'm going to cut this out here. So if you had a minus sine of x, or even a sine of x, it doesn't matter, the sign doesn't matter. But if you had a sine of x in here, okay, you could say that this thing equals minus du over u. Now, in this case, the integral is going to be minus ln of u, right? Because we're doing this, we're getting back here from dx over x to ln of x. Okay, but you don't have this du. You don't have the du. Okay, I'm telling you that the only thing that you have is this one here. So where's the du? You don't have it. So can you integrate this? Yes, but you have to do it by parts, or sometimes people don't even do it by parts. You know, then they gotta use strategies like, oh, we're gonna multiply this by, for example, if you were the secant, okay, let's just say that this is the secant. So this is gonna be, you gotta multiply this thing here by secant tangent, and then you have to multiply here by secant tangent, okay? And then you're gonna transform this whole thing into du over u, and then you can integrate. So integration is not always easy, and because sometimes a very innocent, simple function can be huge. And when I'm saying huge, guys. I'm saying something like, if you had a letter that was this small, it was going to fill this whole page in here, okay? It was going to be like, and keep going and keep going and keep going, maybe 200 steps, 300 steps, to integrate something like this, very, very small. So computationally, that's not efficient. We're going to see some approximation methods, like you remember in the previous video that I showed you some Newton approximation methods, right? You had the x sub n plus 1 equals x sub n minus f of x divided by the first derivative of f of x. So you had this stuff to approximate. You had an estimate here, and you wanted to make a small step. What is the step? It's going to be xn plus a small delta x, which is going to be x sub n plus 1. So these approximation methods are to avoid the integration when it's too complicated. All right, I mean, try to imagine a moon or a moon lander or some kind of spaceship, something that like, I don't know, maybe a satellite. that needs to use these integrations, and the integration is very complicated, it's going to spend 99% of the time trying to calculate the integrals. So it doesn't do that, okay? It just uses approximation algorithms, and as long as the approximation, the steps, and the precision is high enough, the steps are small enough, things are close enough, it becomes feasible for real-world applications, okay? That's what I'm trying to say to you. This is not just a calculus course, it's more of a calculus course with applications, so that's why I keep blabbering here, you know. So, for example, let me think in here. There's a mosquito here. Okay, so the integral of x plus 1 divided by the square root of x dx. Okay, so let's try to do this. What is this gonna be? Okay, I'm gonna separate these things. So you have the square root of x is x to the half. So x, remember x divided by x to the half. These are the same bases. You got an x in here and you got an x in here. So you maintain the base and you do like 1 minus half, which is half. So this is just high school math. So it's going to be x to the half, okay, plus x to the minus half. Yeah. So you got x to the half plus x to the minus half. I don't know, sometimes the notation is like this. That means that you're integrating everything that comes to the left. But I'm going to put the parentheses here. Okay. So this over here is just going to be x to the 3 halves multiplied by 2/3. Okay, why multiply by 2/3? Because you got to divide. So x divided by 3 divided by 2, right, becomes 2x divided by 3. So there you go, right? Plus, and here is going to be x to the half, because you're adding 1, right? Half plus 1 equals 3 halves. Minus half plus 1 equals half. Divided by half, so that's multiplied by 2 plus c. That's that. Okay. Now, you can, the book factors out the 2 to the x, okay? So you can do like 2 to the x to the half. And here you're going to have times 1/3, so 1/3 multiplying this whole thing. And then you have 2x to the 3 divided by 2 divided by 2x to the half. Okay, so it's going to be 1.5 minus half is going to be 1, so there's going to be x, and then you have a plus 1 and plus c. So it's one thing that you can do, right? Well, actually, hold on. Oh yeah, I can't factor it out because this 1 in here, this 3 in here, actually, so you got to do like this, and you got to do a 6 in here, okay? So 6 divided by is going to become a 3 here. There you go. Because you can't factor out different fractions. You got to unite the fractions to factor them out. So the book does this, but you don't have to, okay? You can just leave it the way it was here before. So, let's see here. Now things are going to get a little bit more complicated. For example, the integral of sine of x divided by the cosine squared of x dx. What's the integral of all that? Okay, sometimes you got to rewrite. So you can say the sine, well, okay, you can do a few things. So it'll be the integral of 1 divided by the cosine I'm not going to put cosine of x because it's cosine of x. So, okay, that's the same thing, sine divided by. Now, what is this? This is the secant tangent, right? Because this is the secant. So this equals the integral of the secant of x, of course, times the tangent of x, dx, okay? Now, what is the integral of the secant tangent? Remember, it's the secant. So this is going to be equal to the secant of x plus c. So you see, initially, you're going to be a little bit confused, like, what am I doing here? What should I do? So you got to be rewriting things. Things do get very complicated. That's why they make integral calculators, you know. They create programs that already find certain patterns in equations, and when you have a constant here, or you have a constant squared, or you have an independent variable here, you do this and then you do that, and see if you have a trigonometric function, right? So let's see here. Okay, I thought we're not going to talk about initial conditions, but we are. So the integral of 3x squared minus 1, okay, dx, you do that. So what is it going to be? It's going to be x cubed. Okay, it's going to be x cubed minus x plus c. And you want to find out what this c is. Why is it x cubed, guys? I'm not going to be so annoying like this later. It's just because it's in the beginning. So let's integrate this. So you add this by 1 and you have to divide by this new power. So 2 plus 1 equals 3. So dividing by 3, okay, you simplify this 3 with this 3, and then you have x cubed. That's why we have an x cubed here. Okay, so x cubed minus x plus c, and you want to find out what the c is. What did I say? That without some initial condition, you're not going to have it. All right. So the exercise is informing you that, okay, so this function here is the derivative. Okay, so this we can say that's f prime of x. Now this function here, it's actually f of x. Right? Because we integrated. Great. Now, the problem, the exercise is indicating that f of 2 equals 4. Now you can find it. Okay? Because what do you have to do? All you got to do is to plug in these numbers here. So you say that 4 equals 2. So it's going to be 8 because it's going to be 2 cubed minus 2 plus c. All right? So you got a 6 in here, and then over there you got 4 minus 6, so c equals minus 2. Now we know the c. With this initial condition, we can say certainly that f of x equals x cubed minus x minus 2, because it's a plus c, but c is minus 2, so minus 2. And that's it. I'm going to stop the video here, guys, because I got some other stuff that I have to do, but we'll keep this going, all right? See you guys on the next video.